turn that over, sorry.
Are you ready?
Yep.
I'm Mark Pickrell, and I'm going to be discussing coincidence counting in this series of lectures. My presumption here is that you've already had basics of neutron counting so that you understand a lot of the things I'll be talking about. So that is the underlying basis. One point about coincidence counting is that it is the predecessor and the basis also for multiplicity counting, and I will touch a little bit on multiplicity counting at the end of my talk, only to establish a little bit of overlap in the themes in this talk so that it looks seamless in this series. The fundamental issue here, and is essentially what we'll be talking about for the next hour to hour and a half, is how do you distinguish fission neutrons from alpha N neutrons? And that is the sole purpose of coincidence counting. How do you tell the difference? Neutrons are identical particles. You know that from quantum mechanics. So that you know that two neutrons cannot be distinguished unless they have a difference in energy, perhaps. But other than that, they're indistinguishable particles. And if they're two processes, how do you tell the difference? So let's go into, first of all, what the problem is. The problem is that when we measure nuclear material that produces neutrons, there are two kinds of processes that create those neutrons, and we can't tell the difference. Moreover, we can't tell how much each process is contributing to the neutron total. And without that, we don't have a reasonable way of making a determination of the amount of nuclear material, because we don't know which is making the neutrons and how much they are making the neutrons. Those two processes are the fission process. Now, this is the process we're interested in. This is the process typically of spontaneous fission, where a nucleus simply splits and gives off some number of neutrons. It's actually a distribution can be, in the case of spontaneous fission for plutonium, 0 to 6 neutrons. Notice the difference here. This gives off a single neutron always, without exception. This gives off a distribution of neutrons for plutonium and spontaneous neutrons at 0 to 6, with an average of a little over 2. For for plutonium-induced neutrons, try it again. For plutonium-induced fission, it's about 0 to 8. So the point is you get multiple, typically 1 always. Now, when you do an assay, and if you're trying to determine the amount of nuclear material based on counting these neutrons, we have a problem. And the problem is, how many neutrons are we getting from here? How many neutrons are we getting from there? And if you don't know, you cannot connect the amount of neutrons to the amount of mass. So how do you solve that problem? Let's take a look at some of the obvious approaches you might take. First approach is that the obvious question, is one a lot bigger than the other? Because if one is a lot bigger than the other, let's say alpha N is a 1% effect of the total neutron contribution compared to fission, we can ignore it. Well, here's a nice plot of, for typical weapons-grade plutonium and the various different isotopes, as well as the two isotopes of uranium, of the alpha N rate of neutron production compared to the spontaneous fission rate of neutron production. That is, how many neutrons do you get from spontaneous fission versus alpha N by isotope? And the simple, basic observation I want you to make on this graph is they're about comparable. So you can't just simply dismiss one compared to the other. Actually, in some cases you can for uranium. In uranium, if it's not mixed with fluorine, let's say in a conversion or enrichment plant, you can actually do it for uranium. But in the case of plutonium, you're really out of luck. Well then, what's another possible approach you might take? You might say, maybe, since we're talking about isotopics, if we know our isotopics, the ratio of alpha N to fission neutrons is the same. And if I know that ratio, let's say by an isotopics measurement, then I can go again back to counting neutrons, and I don't have to worry about the alpha N problem, because I can always just back it out from the ratio. The problem is that, as this plot here shows, this is the, and I know this is a bad plot because it was copied from a book, but this is the neutron rate production. This is actually the amount of energy coming off of the alpha particle, which doesn't vary a whole lot. And these are various different materials. This is plutonium on fluorine, plutonium on oxide, plutonium on metal, which is basically has a little bit of oxygen on the surface, uranium on fluorine, uranium on oxygen, and fluorine, and so forth. Log plot here. Point of it is, and this is very, very important, the alpha N production depends on chemistry. Whether it's oxygen, whether it's beryllium, whether it's fluorine, whether it's a metal. And because it depends on chemistry, and you may not know that chemistry, and in general you can't possibly know it very well, all of a sudden you have a huge variable. So you have an alpha N term that's comparable and varying. And you cannot otherwise distinguish the alpha N neutrons from the fission neutrons because they look the same. They're indistinguishable, and they're approximately the same energy. So the bottom line of it is that you've got two sources of neutrons from which you want to infer the nuclear mass, and you can't tell the difference. Now just a little bit of, oh, by the way, I should also point out, interrupt me with questions if you want, and I'm going to stop and ask you questions when I feel like it. And I also have all of this on a PDF file, so if anybody wants a copy, just email me and I'll send you a PDF file. I also have a copy of the software that I use to calculate the errors, the multiplicity analysis using the insulin formalism, and if you want that, I'll send that to you as well, provided it stays inside the group. Okay, let's just talk basically some sort of general background of alpha N, because alpha N is our problem. Fission is what we want to know about, because fission tells us the mass. But both uranium and plutonium decay by the process. Americium-241, which is typically mixed in with plutonium, that's a very, very strong emitter. Neutrons are produced one at a time. Therefore, they are produced randomly. The events are always random, whether it's a spontaneous fission or whether it's an alpha N decay. That's quantum mechanics. Basically, the quantum mechanical process is absolutely random because the uncertainty, because in fact, the quantum mechanical wave functions define only probabilities. And the spontaneous fission has to do with peculiarities of the wave functions in the time domain. So it's an absolutely random process. And we define this term, parameter alpha, as the ratio of the alpha N neutrons to the spontaneous fission neutrons. And we'll use that in some of the equations, but you'll also hear it, so I want you just to be aware of it. Okay, and this is sort of a summary of what I've said so far. Basically, we want to measure fissionable material, because that's what's of interest to safeguards, is fissionable material. And we do that by looking for fission neutrons, but we can't measure fission neutrons directly because they're masked or they're camouflaged by these alpha N neutrons that are occurring at about the same rate and are dependent on so many other factors, principally chemistry, that we can't separate them out trivially. I want to bring up another point here that is a confusing point for many people. In the waste field, if you're measuring, for example, transuranic waste per WIP, you have the same problem, and that's confusing to people because if you look at the WIP regulations, what they want to know is the alpha N decay rate. Because the alpha decay rate, actually, not the alpha N, the alpha decay rate is the measure of the biological hazard of nuclear material. They're not interested in the safeguards application. They're not interested in fissions. They're interested in alpha decay. So you might be tempted to say, well, maybe we don't want to look for fissions for waste. Well, the answer is you do, because the alpha N rate depends on chemistry. So the way that you get the alpha rate is you figure out the amount of fissionable material by looking at the fission neutrons, and then you use isotopics to figure out the actual isotopic distribution that you have, and then you look at nuclear physics to tell you what the alpha decay rate is of those nuclear isotopes to get the alpha rate. And it sounds a bit convoluted going all the way around, but that's how you have to do it. Even though you're measuring, looking for, in the case of waste, alpha decay rate, you do it by measuring fission neutrons because it's not dependent on chemistry. Let's consider the following Gedanken experiment. I have two counters here, and I'm going to stipulate for the sake of discussion that these are 100%, absolutely 100% efficient counters. So if I have a neutron emitted at this counter, I count it. I have a neutron emitted in this counter, I count it. Now they have the following events occur. In this counter we have a fission event occur, one fission event, and it releases two neutrons. Now remember, fission events can release a distribution, but 2 is about the average. It's a little bit over 2, but it's close enough. So this is your typical garden variety fission reaction, and it releases two neutrons for that one reaction, and I count both of them, because it's a 100% efficient counter. So I see 2 neutron counts. Over this counter here, I have 2 alpha N events, 2 alpha decay events, really. And those 2 alpha decay events cause alpha N events to occur. And I get 1 neutron from each of them, and I get 2 neutrons. And just by chance, because it can happen, these 2 decays that happen at the same time. So I see 2 neutrons. So my question is, can I tell the difference looking at these 2 neutrons and these 2 neutrons? Can I tell the difference?
Hope so.
No, I can't. There's no way to tell. There's no distinguishing feature. And I was an honest question. I put the answer down here, which I have to do just to have this thing, you know, so that the view graphs can be made into notes and stuff like that. But in point of fact, you can't. They're indistinguishable. Indistinguishable neutrons and indistinguishable counting event. You see 2 neutrons, you see them at the same time. No difference. So here I've spent 15 minutes now telling you how important it is to tell the difference, and now I've told you you can't tell the difference. Well, the answer is I cannot do it singly, but I can do it in the case of a large distribution. And that sounds funny when you first hear it. It sort of sounds like the used car salesman. I lose money on every sale, but I make it up on volume. In a sense, that's exactly what happens. We cannot determine individual events, but we can over a broad distribution. One of the important things that you need to be thinking about, because it is somewhat non-intuitive, is we're going to start thinking about distributions. And we use those probability distributions. Start thinking in terms of a probability distribution, because we cannot distinguish individual events, but we can distinguish the change in the shape of a probability distribution. And that's what it's about. The probability distribution we're going to look at is something called the Rossi alpha distribution. And it's a particular kind of distribution. Now, we're familiar with, for example, a Poisson or a binomial distribution, for example. This one is a particular kind of distribution. It's an arrival time distribution. And the arrival time is based on multiple and time t equals 0. Time t equals 0 in this distribution is defined as the time that an event occurs. So you have, every time an event occurs is every time you count a neutron. You count a neutron, that's your time t equals 0. And then you count every single arrival time subsequent to that. And you measure the time distances. And you do that for every, again, repetitively for every single arrival time event, every single neutron counted. I'll show you a picture of this and work through it a little bit. What we're going to look for in this is a perturbation in this probability distribution based on the effect of what we call correlated neutrons. Neutrons that were created at the same time, that is, created by a fission event. And then we're going to go into showing how, in point of fact, we can do this. And we're going to do it with, conceptually, these rulers, and we'll show those in a minute. I'm just trying to give you an overview of what we're going to do. Then I'm going to show you how we might do this with electronics. Imagine it as an electronic escalator, which we call the shift register, and show a little bit about the statistics. I also might point out, you'll see another introductory issue I forgot to mention, that these are from the fundamentals course. And the fundamentals course, so we teach this, and this is my original lecture from the fundamentals course. The lecture I'm giving you today is going to be a little bit faster and a little bit more advanced. I've added some extra stuff and a little bit more math, because this is a little bit more sophisticated audience. And this beginning part is following the same thing as the fundamental school. Now, what I'd like you to do is imagine the following. Imagine we have a neutron arrival time pulse stream. So along the abscissa here is time, starting beginning of when you count and going on essentially until you end count. And each little black bar here is the neutron arriving. Now here's what we're going to do. Imagine that I have rulers here. I have lots of them. And imagine now that when a neutron comes in, I start a new ruler, and I put the 0 of that ruler aligned with that first neutron. And then, every time there's a subsequent neutron, I didn't show all the lines going down, I count the subsequent neutrons, and I count all the neutrons that occurred in the first inch of that ruler. Then I count all the neutrons that occurred in the second inch, all the neutrons that occurred in the third inch, and so on, all the way out into the end of when I stop counting. So I'm counting neutrons in each one of these 1-inch bins. Of course, they're 1 inch, they're really a long time, but consider time bins. Now, the second So that process just simply continues. And it doesn't end at 12. It keeps on going until the end of the neutron string, the end of when you start counting. Then I start, my second neutron arrives, and I start a second ruler, and again, this ruler is aligned with this first neutron. And then I count all the subsequent neutrons and find out which bins that they go into. So now this ruler comes in, and I count all the neutrons that are in this bin. And then all the neutrons that are in this bin, and all the neutrons that are in this bin, and so forth. Third neutron comes in, third ruler, aligned with it, counting all the subsequent neutrons in each one of these bins. Fourth one, and I do one ruler for every neutron pulse that comes in. And when I get all done with that, I've got as many rulers as I had original neutron pulses. Now what I do is I add up all the counts in the first bin for the first ruler, all the counts in the first bin for the second ruler, third ruler, and so on. So I add in all the first bins together, and I get a first bin count, summed over all the rulers. And I do a second bin. All the counts, there are two counts in this bin, you can see them there. All the counts in the second bin, all the counts in the second bin, this has one. All the counts in the second bin, I didn't bring them all down, but it has some. All the counts in the second bin, add all those up. All the counts in the third bin, and the fourth bin, and all the way out until we don't have any more counts. So now I've got, as a function of bin number, a number of counts. So I've got a plot now that I could plot. How many counts do I have in bin 1? How many counts do I have in bin 2? How many counts do I have in bin 3? This is the sum, bin 1, 2, and 3. And I plot that. So now I'm going to ask you a question. What does that plot look like? And then I'm going to ask you why. Say it. It's flat. Why? That's the correct answer. Random. Can you give me a little bit better answer than that? But you're right. It's random.
At rival time is rendering student.
Okay, you're very, very close. We have some people that are close to, just got out of graduate school. Let me ask another question. Well, you're absolutely right. The simple direct answer, if I take a look at it and plot it, it's flat distribution. It's not exactly flat. Why isn't it exactly flat? Because it's random. There's statistical fluctuations, and the statistical fluctuations are 1 over n, 1 over root n, the number of counts. Okay. Putting it in a little bit different words, the reason that it's flat is that there's absolutely no preference in this system to pick one bin over another. There's no reason to prefer one bin over another. Why should bin 6 have more than bin 13? Why should bin 1 have more than bin 50? There's no basis for preference. Now, that's a hand-waving argument. There's a more formal argument. And we have some people that are just out of graduate school. So you just took your general exams. Okay, now in your general exams, you have a system, which is a statistical system. What is the ratio of the statistical probability if there were, let's say, a preference compared to a flat? What is the reason this thing is flat? Give me a hint. What would happen if I had them all concentrated to the probability distribution, the statistical microstates? The function omega. Not going to win this. All righty, fine. Second law of thermodynamics. The distribution of this can be considered the omega function in statistical mechanics. It is the distribution of available quantum mechanical microstates. The simple fact is that if I were to have some kind of a concentration, the available number of microstates would be reduced, therefore the entropy is reduced. If you have a random process, you cannot reduce the entropy. Second law of thermodynamics. Entropy can only increase or stay the same. You cannot create an ordered system from a disordered process. Second law of thermodynamics insists that given the underlying stochasticity of the problem, these neutrons in time are going to distribute themselves evenly because that is the maximum entropy state. Second law of thermodynamics. That's the formal definition. So we're guaranteed a flat distribution except for the normal statistical fluctuations due to the fact that it is a random process. Okay, now, I I told you that neutrons are indistinguishable, but we're going to color them anyway. So we had a random pulse stream of black neutrons, which means they came from purely alpha n sources. Okay, because they come one at a time and it's a random process. And I'm still going to do my process of aligning up my rulers, but I'm only going to align up my rulers on the black neutrons, that is the ones produced randomly, those that are produced by the alpha n process. But I'm going to now allow that we're going to turn on a fission. So now fissions can occur. And these are somewhat idealized fissions. Instead of having the 0, 1, 2, 3, 4, 5, or 6 neutrons per fission, all of these fissions give us 2 neutrons. It illustrates the point. We'll reintroduce the complexity later. So now we get pairs of red neutrons, where the red neutrons correspond to fission events, black neutrons to alpha n events. Black neutrons are entirely random. The occurrence of a pair of red neutrons is that random as well. Yes, exactly. And I use my words carefully. The occurrence of the event of a pair of neutrons taken as a unit is also a random event because spontaneous fission is random. So these things here are distributed randomly. Okay, now we go through the process, and again we line up the neutrons, and then we line up the rulers rather to each neutron. But I don't line up the rulers to the red neutrons. But I do count the red neutrons. Okay, I'm doing this in stages. We don't actually do that in electronics. We can't tell the difference between red and black neutrons. But I'm building this up in stages. So I align my rulers only to black neutrons, but when I count the neutrons in the bins, I count both red and black neutrons. What does my distribution look like? Anybody? All right, is it still flat? No? Yes, it is still flat. It is still flat because the events of the fission events also occurred purely randomly.
It's just a sum of random events.
It's just a sum of random events again. So now we're getting pairs of neutrons, which may be adding 2 counts in each one of these bins, but they're distributed randomly, just like the alpha n. The alpha n single neutrons are random. The fission events, event as a pair of neutrons in this idealized case, is a random event. So you get a flat distribution where the pink here is the alpha n neutrons, and in this particular example where I've just shown the red neutrons, the fission neutrons that you count now actually sit on top of that as well. And that's for the particular ratios I've picked. You could pick different ratios and they could be different. The only point I'm trying to make here is that the distribution is still flat and fluctuating. All right, now let's do what would be more like in real life. Now, I'm going to consider the same pulse stream as we did in the previous case. Cut and paste. And I'm still going to count both red and black neutrons, just like I did the last time. But this time, I'm now going to align my rulers on every neutron, red or black. Doesn't matter what. If it's a red neutron, I'll have a ruler that goes to it, like I did here and here and here. Black neutrons as well. Black neutrons, red neutrons, all neutrons, because they're indistinguishable anyways, I can't make that difference. I'm going to align a ruler and I'm going to count. Question. Now what does the distribution look like and why?
Help me out one more time. You're going to align the rulers to any event, not
Yes.
just the...
All events, yes. Does it look, well, let me ask a simpler question. I'll leave that there. Does it still look flat? If not, why not?
Is there a preference for the first bin?
Yes. There's a preference for the first bin. Because the second fission neutron always comes right after the first one, because they're produced at the same time. The second neutron is not a random event in a fission event. It comes after the first one. It is correlated, not random. The event itself occurs randomly in time. The time when the first neutron occurs, obviously, is random in time, but when the second neutron occurs in a fission event, it's correlated to the first one. Therefore, there's a preference. Therefore, you're going to see more counts in the early bins. Have I violated the second law of thermodynamics? If not, why not? If so, why? I made the point that you wanted to occupy the maximum number of microstates. Clearly, now that I have a concentration here, I have a reduced number of microstates that I'm accessing. Have I violated the second law of thermodynamics? Why not?
I'll answer the first half of that. No, you have not.
Okay.
And I'll leave it to my colleagues to finish up.
No, I have not. All righty. The reason I haven't is that, by the way, in this case, I have not violated the second law of thermodynamics. Has entropy increased? The answer is no, but it hasn't decreased either, because the neutrons were born together. They were born correlated. Therefore, the fact that I detect this decrease in microstates doesn't violate the second law of thermodynamics. I haven't gotten a situation where I've concentrated more than they were already born. They come together as a unit. The fission event is a singular, isolated, individual event in time. Those neutrons come off right at the same time always. Now, this isn't part of this lecture, but it should have been part of one of the earlier ones. The two neutrons are created at exactly the same time. Are they detected at the same time? If so, why? If not, why not?
They're probably detected at the same time because you probably don't have the electronics to distinguish between the two. Fission occurs 10 to the minus 14 seconds, so chances are you're going to see them coming exactly at the same time.
Is he right?
What's your detector? Well, they would be moderated.
Polyethylene and helium.
They would be moderated.
Yes.
So they will go through the whole process.
Exactly. Exactly. The answer is you don't. And it's not that they weren't born at the same time. 10 to the minus 14 seconds. Thank you. I didn't actually have that number on the top of my head. But what the die-away time or the detection time, same thing, because it's an exponential. It's convolution. The detection time is typically, what, 50 microseconds? Sort of a canonical number. So these things are going to be spread out by typically 50 microseconds. Now, they're not going to be separated out exactly by 50 microseconds because, remember from the neutron lectures earlier, the die-away time of a detector is the exponential. The convolution of an exponential is an exponential. So your detection time is 50 microseconds. The separation time between two neutrons is also 50 microseconds because it's an exponential. So what you'll see is a preference that these things will occur early, but that preference will die away as the exponential with the die-away time constant, or the detection time constant, due to the moderation in the neutron detector. Now, if you did not, and that was implicit in it, but all detectors have some kind of die-away time. The helium-3 moderated by polyethylene is typically 50 microseconds. There are obviously these scintillation detectors that Phyllis Russo and others are working on that have much, much shorter die-away times, but nothing detects anything instantly. So there is some spreading out of this because of the detection. Now, I've color-coded this, so the pink are the alpha N neutrons. This turquoise, I guess, are the fission neutrons that are detected as random events. That is, the fission neutrons detected when the rulers are aligned with alpha N events. The green are the neutrons detected preferentially when the rulers are aligned with the first of the two fission neutrons. And the preference is the fact that the second one is within a die-away time of the first one. So now, let's conceptually talk about how we might measure fission neutrons. Fission neutrons are the ones that come in these correlated pairs, and only fission neutrons. And we want fission neutrons because fission neutrons gives us fissions, and fissions tells us how much fissionable material is. And from these measurements, the green tells us something about these fission neutrons, at least the second one. So the green numbers here is the measure of these correlated pairs of the red neutrons. And that's what we want to know. So how do we measure it? Now we know that this thing decays away exponentially with the die-away time or the detection time of the detector, basically the characteristic time that that a neutron moderates and then transports to the detector. It's really, one qualification of what you said it was moderation. Moderation in polyethylene takes about a microsecond. It's actually the diffusion transport once you have moderated into the helium-3 detector. That is the characteristic time. But we notice the key element before is that the rest of the distribution is flat. Flat but fluctuating. And so the basic principle is this. If we counted a block here in time with rulers, and then we counted a block here with rulers, and we subtracted this from this, we're left with a green to within the statistical fluctuations. Which is to say that all this stuff here, we don't care about because we don't use it. And we don't need actually this fine-grained stuff here either. We just need a block here and a block here, and we subtract the two. And those of you that are familiar, this is called the reals plus accidental gate, and this is called the accidental gate. The green are called reals. Can you ever measure a reel directly? Can you ever see a reel?
Only late at night.
You can never see a reel. Now, I've drawn the pretty picture with the colors to talk about how the different neutrons came. Let me ask the question a little bit more carefully. Can you tell the difference between a green balloon and a pink neutron? No, of course not. They're indistinguishable. The only thing that I know in this plot is the sum totals, the top values here, and the top values here. But if I count a neutron in here, I don't know whether it's a pink, a blue, or a green neutron. I don't know. If I count a neutron here, the only thing I know is that it's not a green neutron. That's all I know. Okay. So basically, the problem now has devolved into, we want to measure the green. That's what we're about. Now, we'd like to do this with these electronic rulers that I just talked about, except that it doesn't take too much conceptual imagination to realize that that's an impossible problem practically. If you have a pulse stream 1 billion pulses long, that's 1 billion electronic rulers that, even with modern technology, would fill up this room. So we're going to find a way of implementing the electronic rulers without a huge amount of electronics. It's called a shift register. So let me talk about the next thing that I'm going to teach you in this lecture. What are we going to do? Well, I want to show you, we're going to discuss several parallel threads. And I'm going to show you they're all equivalent. So at the end, you see that they're all tied together as one. The green from the rulers. Because the green is important, because that is what's tied to the fission events, which is tied to fissions, which is tied to the fissionable material. And I'm going to show that you can get the green from the shift register, but I'm going to cartoon explain it with an escalator. We're going to show that if you actually were to understand what coincidences are, we'll just go through and look at what coincidences are, and it's common sense, that the green are actually not neutrons, they're coincidences in terms of the numbers. And that there's a simple factorial formula that comes from it, which is basically comes from the combination. And we'll talk about that. And I want to emphasize again, because it's a little bit counterintuitive, we were thinking the green was just the number of second neutrons, but it's really the number of coincidences by the fact that the rulers happen. Why is that? Can you think why that might be? Why the total green is the number of coincidences, not just neutrons? Why that has to be? Or let me ask a different question. Let's consider, it's an important theoretical, conceptual point, really. Let me go back here a little bit. Say, go way back. Take this case. Can you think why the pink, the original flat distribution? So this is the one, the first slide that I showed with the rulers, and we got the pink distribution, the one that was flat originally. Why is the pink distribution not the number of neutrons? Why can't it be the number of neutrons?
Do you have some ideal detector or something, or?
Assuming an ideal detector, yes.
I mean,
you're not counting neutrons. You're starting a bin, and if no other neutrons occur in that bin, what if they do? Because we're counting something in those bins. All right, I'll give you the answer. How many times, ultimately, do I count that neutron?
Many different numbers.
Yes. Let's say this neutron here, because I forgot where I pointed the last time. How many times did I count this neutron? 1, 2, 3, 4, 5, 6, 7, well, 10, 15, whatever. You count each neutron many times in this process, and some more than others, depending on where they occur in the pulse stream. So all I'm trying to establish by this is that these counts in these bins are not, even though the original pulses were neutrons, the sum totals cannot be neutrons. They have to be something else. You can count them multiple times. So there's some multiple count of neutrons. Okay, and I want you to consider that because we're counting things multiple times. Now, hold that thought. We'll get back to it. Let's consider, moving on to a different story, hold the thought of the rulers in the green. Let's move on to a different subject, the shift register. I want you to imagine an escalator. And we have an escalator. We have a couple of people here running the escalator. This lady down here counts the number of people on the escalator because she knows when it gets off. And this lady here counts when somebody gets on the escalator, and these are neutrons, or there are other people getting on and off the escalator. So the question is, you have this line of people arriving, let's just say randomly, doesn't matter, and they get on the escalator. So they step on the escalator, so this first person is going to step on the escalator, then ride the escalator down and get off. This person is going to keep track of the number of people that are on the escalator at any one time. So when somebody gets on the escalator, she keeps track that the number has gone up. When they get up off the escalator, she drops the number by 1. So she always knows the number of people on the escalator at any instant in time. This person sums up the total number of people that are on the escalator to a running total every time somebody steps on the escalator. Just before, but the person stepping on the escalator doesn't count. Okay, they trigger the count of everybody there before them. Okay, so I want you to think what's going on here in terms of the mechanics. This person's keeping track. This person is triggering. Okay, first person right here, about to step on the escalator. How many people are already on the escalator?
0.
0. So, 0 plus 0 is 0. Total count is 0. Okay. Second person comes along. First person's riding down the escalator. Second person comes along. They step on. How many people are on the escalator? 1. Okay, so this person says there's 1 person on the escalator. This person says, I now have 0 from the first case plus 1. 0 plus 1 is 1. Third person comes along. Now there are 2 people on the escalator. Third person's about to step on. The count is 2. 2 plus 1 from the previous case plus 0 from the previous case is 3. I'm going to show you this is going to get us to the green here. This is a ruler. We'll get to that. Finally, the last person steps on the escalator, and there's 4. And there could be more after this. And then some of these people are going to be coming off, and so the count will be going up or down. So at any time, the count is a running count of the total number of people already on the escalator. Now, the escalator is moving at a fixed time rate. You know how an escalator is like. So, but between the time that a person gets on and the time that they get off is a time. It's the time that you ride the escalator, because it's at a fixed velocity. So think of it as a time bin, like a ruler time bin. Okay. Now, go back to this one. Think of this escalator as a shift register, being clocked along at a fixed clock rate. Okay, so every time somebody gets on, they just ride the shift register, which shifts them down. And so the same thing electronically is that you could have this person here counting the neutrons in the escalator, or counting the pulses of the neutrons in a shift register. And every time somebody goes into the shift register, the count goes up, and then you go to the shift register, and every time they come off of the shift register, the count goes down. So this is an up-down counter. You get on, it counts up. Shift register shifts you up, you count it down. So the shift register counter, an up-down counter, keeps track of the number of people on the escalator. Then there's an accumulator. Every time somebody gets on the escalator, not counting themselves, of course, you sum up in an accumulator, adding each time the number that's in the count, the numbers that are in the escalator at that time. You just keep summing it. So we call that a shift register, or an escalator. And this is just a summary slide in case you want a hard copy of exactly the process I just described. And you can do it with electronics. So I can do the electronic shift register, and I can do that to emulate the escalator. That's nice. Hold that thought. Let's go to something else. We'll get back to it. Let's consider the way we count coincidences. And let's just say everything pulse that I have up here is together in whatever time bin that we're going to define. So, the question is, if I have a single solitary pulse, actually I should have one up above. If I have no pulses, how many coincidences do I have? None. Kind of a trivial case. Obviously, trivial case. If I have one pulse, how many coincidences do I have? Coincidence being a pairing. Well, with only one of two necessary, you have 0 coincidences. Now here's the next one. If I have 2 pulses, how many coincidences do I have? Well, it's 1 pairing. Now some people, and this is an important point, I'm going to take a slight divergence here. Some people would say that I have 2 coincidences in this case. I have this coincident with this, and this coincident back with itself. And when you count coincidences, you can choose a convention, which means you can pick one way of doing it or the other, so long as we all agree. Does this count as 1 or does it count as 2? Doesn't matter. Doesn't matter in mathematics, but whatever you do, you have to be consistent. So pick one and stick with it. Okay, I'm going to do that. This is one coincidence. I just decided. Actually, I didn't just decide. It was decided a long time ago. But I want you to understand that it was a point of controversy, and sometimes you'll see factors of 2 floating around the equations, and I want you to know where it comes from. And that there is no fundamental problem with one or the other. It's a convention. But you need to pick one and stick with it. And what we do in this group, one that has been picked, that's one coincidence. Okay, that's a little bit of a divergence. Now we have 3 neutrons. This is 3 coincidences. And you can see the little arrows, what the correlations are. And if I have 4 neutrons, you now have 6 coincidences. And you can look out for this yellow arrow here. So you have this with this, 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 and this with this. Total of 6. Okay. Now, trying to pull this all together. I'm trying to show that the shift register, remember that escalator? It counts coincidences. I'm showing that the green are coincidences. We know that they're not neutrons. And I'm trying to show, given what we just defined as coincidences, that you have a simple formula for it for here. I have a slide on that, and I'm going to do that next. And for this audience, it's a little bit trivial. And all I've done is try to bring this together. Let's talk the formula first, the nu minus 1 over 2. That is simply the combination formula from combinatorics. It's n factorial over n minus r factorial, r factorial. R is 2. It's a combination of n things taken 2 at a time. And that is the formula you get, and that's the number of coincidences you have. Okay? You're looking at pairs. Excuse me?
N over K, whatever.
It's n factorial, right, but you're thinking of the permutation over k factorial permutation, but it's not. It's n factorial over n minus k quantity factorial, k over k factorial. That's the combination of the permutation. So you have that extra denominator, the k factorial in the denominator. Point being is that this is combination. It's just simply how do you get pairs of things in a group of stuff? I have a bunch of things happening at roughly the same time. How many pairs of them? That is exactly what I did here. That's the definition of a combination. So this is a little bit more sophisticated audience. So I didn't put this in there, and I should have. In any event, let's imagine. So let's go through this and say, let's just go through this numerically. I have a number of neutrons going from 0 to 5. Back from our little analysis here, we know how many coincidences we have. Okay? And we did that before. 0 neutrons, 0 coincidences, 1 is 0, 2 is 1, 3 is 3, 4 is 6. I didn't do it, but you could figure it out. 5 is 10 coincidences. Not surprisingly, the formula for combination, which is this here, gives us the same set of numbers. Now, the shift register, or the escalator, does the same thing. 4 neutrons gives us 6. You can imagine 3 neutrons gives us 3, 2 neutrons gives us 1, and any fewer than that gives us 0. So the shift register, or the escalator, isn't counting neutrons, it's counting coincidences. Now, the interesting thing is if I took a ruler and did the same thing, take the ruler and do the same thing. That's many, many neutrons. But take the first 4 and do it. So let's say I have only 1 neutron. I have 1 ruler. How many neutrons are in any of the subsequent bins? 0. And assume now we're taking a big bin. I just want to see, I don't care what the time window is. If I have 2 neutrons, I have 1 ruler. The first ruler goes with on the first neutron, sees the second neutron in the bin. Count of 1. Now I have a neutron on the second. I have a ruler on the second neutron, but there are no more neutrons after that, so I don't see any more. So it's 0 plus 1. Now let's say I have 3 neutrons, so just those 3. I have 3 rulers. First ruler sees aligned on the first neutron, counts the subsequent 2 neutrons, plus the second neutron, the second ruler on the second neutron counts now 1 neutron. 2 plus 1 is 3. Third ruler on the third neutron now counts no more neutrons. 2 plus 1 plus 0 is 3. It does the same thing. And the point I'm trying to show is simply that what the rulers do is the same thing as what the escalator does. And the way that you can think of it is like this. The ruler bin that we can pick aside is the length of the escalator. And so what I'm doing is I'm putting the multiple rulers is just this escalator cycling through, because the escalator cycles through a test bin. And I don't need to have rulers with all of those bins. All I need is 2. 1 plus the reals and accidentals to get most of the green, and 1 to get way, way out there where the distribution is flat, so I can subtract the 2. So I need a 2 bin ruler now. And the fact that the escalator cycles it through is how I get the multiple rulers. And I just wanted to show that you get the same numbers. So what we've done with the shift register is back to the original problem. We want the green. We get the green because we can't tell the difference between green, blue, and pink by measuring the total amount here, integrated, subtracting the total amount here. Those are equal signs, done with effectively 2 shift registers. We actually can cheat and do it with 1 shift register and a little bit of counting. And here's the shift register circuit. Neutron comes in, there's a tiny bit of pre-delay, goes into the shift register, and it starts getting cycled through. At the same time, it increments the up-down counter. When it comes out the shift register, it decrements the up-down counter. The up-down counter gives us the total number of neutrons pulses in the shift register. Then the strobe comes in, the same input. This pre-delay makes sure, basically, that the neutron that triggers this is not counted itself. The strobe comes in and immediately triggers the reals plus accidentals counter. That's the first one. It gets triggered right away. then there's a long delay, and you trigger the accidental scalar because it's way out in time. Now, let's add one layer of complication. When I discussed this, I talked about the sort of idealized fission, the idealized fission being it gives off 2 neutrons. Well, it doesn't give off 2 neutrons. It gives off 0, 1, 2, 3, 4, 5, or 6 in the case of plutonium. So how do I, now going to complicate that a little bit. We don't know how many neutrons were released, but we do know the distribution, and we can take the average over this, the expression that we have for the number of coincidences. And we know that the number of coincidences is combination formula, nu minus 1 over 2, where nu is the number of neutrons released. Straight from the combination, straight from the thing. And I can average that over the distribution of the number of neutrons that are released. What is, can you think of what this term actually corresponds to? If nu is equal to the number of fissions, if nu is equal to the number of neutrons released in a fission, what is this summation equal to, conceptually?
Well, it's P is probability.
Yep. Can you get a sense of it? What is this total number? It happens in one fission, pardon me?
I would guess it's the number of fissions coming, or number of neutrons coming off fissions.
No.
Is that close?
That's nu. No, that would be average of nu. That's the number of neutrons coming off of a fission, average over the distribution.
Okay. Do I get partial credit?
Nope. It's the number of coincidences released by a fission. You almost could think of it as, it's an imaginary concept, but it's an easy construct for conceptual understanding. This is the number of coincident particles, imaginary particles, coincident particles released by a fission. Here's the number of fissions given the number of neutrons. Here's the probability of that many neutrons being given off at a time, and you sum over it. This thing has been normalized, by the way. That's the number of coincidences you get per fission. Okay. Now let me tie it back into the mathematics. What we know is that the green is a measure of fissions. More fissions, more green. We know that the shift register measures the green by measuring everything under the green, blue, and pink and subtracting out the pink and the blue, giving us just the green. Not all of the green, but most of it. We'll show that in a second. So somehow we've got to connect the mass to the green, or more appropriately, the green to the mass, because we measure the green. We get a number for the green. It's called the reals. What we want is the mass. So let's go through this equation. This is the standard coincidence equation. The mass of plutonium-240 equivalent. I'm going to use plutonium as the example. We're going to use the plutonium-240 equivalent, meaning that we have several isotopes that are spontaneously fissioning, 238, 240, 242. We talk in terms of a Pu-240 equivalent. That should have been discussed in your earlier neutron lecture. So the effective Pu-240 times the number of fissions per second per gram, which gives us the mass times the fission rate is the total number of fissions that we're actually getting. That's the number of fissions. Now, that gives off, probably this, I needed to do these graphs differently because what I really wanted to do is talk about this term next. So we've got the number of fissions. I'm going to go back and forth. But for the number of fissions, what does this term here tell us? The number of coincidences per fission. So this term, which we talked about before, times this term is the total number of coincidences per second for the given mass. So do we detect all of those? The answer is we don't, because we have an efficiency. So those neutrons coming off as two neutron pairs, right, coincidences, we only detect them. So we've got to consider an efficiency, and the efficiency is epsilon. and we detect the first neutron with efficiency epsilon, and we detect the second neutron with the same efficiency epsilon, and we've got to detect them both so it's the efficiency squared. And the last issue is, do we count all of the green? And the answer is we don't. Let me show you why. Here's our green. When does an, now this one I know you know, so somebody's going to answer me, we're going to sit this out forever. When does an exponential go to 0?
Depends what you mean by 0.
No. When does it go to 0?
Never.
Never.
But
Thank you.
practically...
No, yeah, right, I know. Practically nothing. It never goes to 0, ever. Which means, can we ever count all of the green, since the green is decaying away exponentially?
No.
No. So we only get some of the green. And we've got to count, how much of the green do we get? Well, that depends on how big we want to make this gate. Do we want to make the gate small, or do we want to make the gate big? Now, as you can infer, there's probably an optimized level of gate size. And I'll talk about that conceptually. You can work out the math pretty easily. But clearly, the bigger the gate we have, the more green we get. But we don't get it as fast because the green is decaying exponentially. So, if I have my gate here, and I wanted to double it to here, the amount of extra green I get is very, very small. Finite, but small. But if I make that gate bigger, I make this gate bigger too. And therefore, I've got more of these statistical fluctuations happening.
You have more error than...
I have more error. So getting green is good, but getting error is bad. And so there's an optimal size of this thing that gives you the maximum green and the minimum error, or the minimum error overall. So we pick it. I'm not going through the math of that. But the point is that in the formula, you have to correct for it. This, 2 exponentials are the correction for that. This is the exponential of the pre-delay, that is that little bit of delay right on early, where you miss a little bit of the green right early on. Pre-delay is typically 3 or 4 microseconds, time constant is 50, so it's not a big effect. Minus the part of the green at the end where you stopped counting, where G is the gate width, and T is, again, the die-away time. Typical fractions of this thing, this whole term here, like 60 or 70%. And it's just an optimized number of gate width to get the minimum amount of noise, but you do have to correct for it in the formula. And there's the formula that gives you the number of greens counted as a function of the mass, which is what you want. And the number of greens is simply the reals plus accidentals gate minus the accidentals gate, giving you the reals. I hate the notation of this, using a single number as an R plus A. I always have hated that notation. But it is a single number, and it constitutes both the accidentals, which is the pink and the green component, plus the pink and the blue component, plus the green component. And that ties the whole thing together. Okay. Now I'm going to go on for about another 10 or 15 minutes. I'm almost done. I wanted to touch a little bit on multiplicity counting, and just so that it's seamless with the next discussions. It's an extension of coincidence counting. It measures, adds higher measurements of higher order moments, meaning we've talked about counting single neutrons, that's the totals, and pairs of neutrons, which are called coincidences. Now we can consider counting triple neutron events. 3 at a time. And it does the shift register to do it. And it's a modification of the shift register. It looks like this. You've got an up-down counter, and this time, instead of counting the total number in the up-down counter, you count the number of cases that you have 0 or 1 or 2 or up to 256 in this up-down counter. Other than that, it's the same. And then you use the knowledge of what you're doing and basically taking the factorial moments, and again, that's the next lecture, in order to go calculate the singles, the doubles, or the triple events. I also wanted to talk about making a connection between the formulas that we've shown. You will see the doubles equation, which is shown here in multiplicity counting, and doubles are equal to reals. They're one and the same thing. And you'll see this formula a lot, and I wanted you to be comfortable with the fact that this formula is consistent with the coincidence formula that we just derived for the reals. And I've just done this term by term. But basically the mass is equivalent. The F is the fission rate, which is basically the number of fissions per second per gram. And by the way, sometimes you'll see this formula written where this is equal to just the F value. It's just a notational convention. But I want you to know that it basically comes in here. The efficiency goes directly to the efficiency. F sub d is called the doubles gate fraction, and it is equal to the exponential, the fact that you're only calculating part of the green. It's called the gate fraction. Nu S2 is equal to this number of coincidences that we talked about before, the sum over the combination formula of the number of coincidences. And then the 2 and the 2 go together. So where do the two formulas differ? Well, obviously, this equation has this term here, and it has that term there. M is the multiplication. Multiplicity is typically used to measure mass in a multiplying environment. So the multiplication is non-unity. It's greater than 1. Coincidence counting explicitly assumes that multiplication is equal to 1. Now, there's something called the known alpha method for which that isn't true. That's also not in the scope of this lecture. But basically, if you set m equal to 1, that term disappears. M equals 1, 1 is 0. This term disappears, and you see that those two equations are the same. And I just wanted you to see that, so that you didn't feel that there was some kind of inconsistency between the two formalisms. Finally, I want to talk about precision measures. And people will discuss the fact that multiplicity is this great, great benefit. And in most cases it is, but it isn't always. And the reason is that multiplicity typically suffers from higher precision errors in coincidence counting. So I wanted to talk a little bit about the scaling and also the magnitudes of the errors that you get with totals counting, coincidence counting, and multiplicity counting, and a little bit of the math behind it, although not all. So here's a nice plot that I generated with the Ensslin figure of merit code, showing the percent error for a nominal case. It's like a 25% efficient counter, alpha equal to 1, just a nominal case, where I scale the sample mass in grams of total plutonium for weapons grades. And it didn't plot out very well, but it goes to, tenth of a gram, a hundredth of a gram, a thousandth of a gram. And then it goes up here, that's 1,000 grams, 10,000, 100,000, a million, 10 million grams, or something like that. So it's a big, long range. It's a log-log plot. And here's the precision only. Here's the totals plot. Anybody know how the totals precision scales? This is relative error. 1 over square root of n. Is it equal to 1 over square root of n? If so, why? If not, why not? That's a hard question. I actually got this wrong in a talk I did a few months ago, which is why I'm asking you.
I can answer the first half of that.
What?
No.
No, it's not.
I'll leave it to my colleagues to finish that.
Yeah, all right. It's not because, consider the totals. The total, assuming the total's error is 1 over square root of n, that is predicated on it being a Poisson process. Okay, that is, you have a binomial distribution of a Poisson process, and then you can simplify that into a Poisson distribution, and from that you can derive that the error is, or the uncertainty is 1 over the square root of n. Is the totals production in any one of these systems a pure Poisson process? No. No, why not?
Because of the randomness of decay.
Randomness of decay?
Because part of it is not random.
Yes, what part isn't random?
The second.
Yes. There are fission events. Those come as pairs of neutrons. And that's a single random event, but you're getting 2 counts. So the point is the number of counts and the number of actual random events is different for those fission events. That's exactly right. So it scales as 1 over n, or 1 over root n, but it isn't equal, but it's generally close. Okay, now the coincidence counting comes down, also scaling as 1 over root n, and then it flattens out. And the multiplicity counting comes down 1 over root n, and then it actually turns around and goes back up again. Why would coincidence counting in this region here have a higher error than totals counting, and why would coincidence counting, why would multiplicity counting have a higher error than coincidence counting? Any sense?
Well, you explain as multiplicity require multiplication, right?
No. The answer is actually real simple. Here you're counting totals, so you only have the totals error. Here you're counting totals and coincidences, so you have the totals error and the coincidence counter error summed in quadrature. It's got to have to be more, because now you've got two. Here you've got the singles, doubles, and triples, totals, coincidences, and triples, all of which have errors now, all of which have to be summed so they're higher. And that's the general reason for the scaling, that you've got more things contributing to your error.
No, I was confused that this is I thought it's a double, not a coincidence. And you explained in the previous slide that double accounts for internal multiplication.
Right. This whole thing is assuming multiplication is 1.
Oh, okay.
And a double and a coincidence are identical in terms of what they are. The double's equation in multiplicity includes the multiplication effect. The doubles and coincidences are identical.
Right.
There's different terminology used in different contexts. Any sense of why this thing flattens out and this thing goes up? What's happening here? When we calculate the error for coincidences, and I don't know if you've done this in the laboratory or not, but the coincidence error is really the sum of two errors because we're having two gates. We calculate the reals plus accidentals gate, and we calculate the accidentals gate. And so we actually have two counts now. And some people like to write that as the reals, which we actually end up inferring, and the accidentals, and it's r plus 2a. So we have two counts. In the case of totals, we just have totals. But in the case of coincidences, not only do we have the green, but we have the effect of the accidentals. So in the case of totals, it scales, whoopsie, I screwed this, 1 over square root of n. Sorry, that's an error in my view graph. That should be square root of n. But consider the case of coincidences is that we have the accidentals. And the accidentals are fluctuating. Remember, that's the pink and the blue? And we talked about the size of the gate because if we made the gate big, we get more of that error. But we've got to calculate that error. And that error is the accidentals rate. Now, the accidentals rate is easy to figure out. Consider S, this is a convention for singles, so I'm using multiplicity convention, the totals rate, number of single neutrons per second. The higher this number, the more neutrons are going to be on the shift register at any time, because it's denser. If the shift register are fixed length and time, then the higher this rate, then proportionately the more neutrons in the shift register, which means every time you count them, you get a higher number. But also, the higher number of times, the faster rate that you trigger the shift register. So you have two factors. So it's the accidentals rate, and I'm assuming these are uncorrelated now, is going to be proportional to the totals rate squared times the gate width, which is the length of the shift register, times the total time, because I'm converting that to a total count. And the significance of this, then, is that your accidentals rate is proportional to your totals rate squared. And I'll show you how that enters in. In the case for error and coincidence, again, the error is equal to square root now of the r plus a gate plus the a gate, right? Going back to basic Poisson statistics, sigma squared, we're actually, if sigma is equal to square root of r plus a and sigma accidental is equal to square root of a, then adding these things in quadrature is the square root of the sum of the squares, so it's r plus a plus a. If I substitute in for that the actual values that we get, where d is the doubles, I get d times the time, that's the reals, plus twice a, which is 2 times the gate times the time, times the totals rate squared. And if I make that a relative error, then I divide that by the total number of reals, doubles times the time. And this is the sigma rel, the relative error that I'm plotting here. Whoops, not plotting there. Plotting here. So I'm plotting that value. Now, what happens is that, remember, that the S is the totals rate. That's going to be roughly proportional to the mass, all other things being the same. And this plot is what I saw before. So let's now actually solve it analytically, and you can only solve it analytically easily for the two limiting cases. If you have a low level of mass, then your S is a low value. Small mass, small totals, F squared now gets smaller faster than D does. So this term is smaller, and this thing simplifies to 1 over the time times the epsilon times the mass. 1 over the square root of mass. 1 over the square root of n. Which is exactly what we see. For small masses, it goes right as 1 over root n, just like it does for totals counting. Different factor, but same scaling. Now consider the opposite case. Now you've got a lot of mass. Now, S squared, because the square gets bigger faster than the linear term, S squared gets bigger faster than D gets bigger with large mass. So now 2 dt S squared is much larger than dt. And again, simplifying it, you get an equation, this equation here, this is the die-away time, the efficiency, and the total count time, but it's constant in mass. So what happens is that just as we saw, at low masses, we decline as 1 over root mass, root n, and then it levels out and it becomes absolutely flat. That's what we saw. And I just wanted to go through that analytically so you have a sense of the bounding values of coincidence counting. Increased mass is sort of the intuitive sense. Increased mass, more counts, better error. Certainly works with totals counting. Doesn't work with coincidence counting. There's a limit because of the accidental effect. I haven't shown the calculation, but the similar calculation, because now you're doing singles, doubles, and triples, and multiplicity counting, actually turns it back up. We're done. Any other questions? Yeah.
I find these 3 devices very weird. Shift registers, rulers, escalators. So historically,
Pardon me, shift registers, rulers,
escalators.
Okay.
Historically, how they evolved?
Well, the shift register, it's interesting. Intuitively, this thing was backwards. They started with the shift register, and then about 10 or 15 years ago, we started explaining it with the rulers and the escalators at the same time. The escalator is an obvious illustration of the shift register, but a lot of the conceptual understanding came after the actual shift register was implemented, because a lot of the math had been done first and people were working from the math maybe without the complete understanding of perhaps the intuitive understanding, I should say. And so it evolves. It evolves sort of backwards from how I presented it here. Yeah.
In the formula that relates the mass of 240 to reals, how can you assume that the reals are all from just the fission of 240 unless you know for a fact that your sample is pure? I mean, you're not, how do you discriminate the fissions from other isotopes that might be there?
You can't. And that's what we talk about, and I'm sorry if I didn't make that clear, I went over pretty fast. If we talk about P240 effective, which is the 240, 238, 242, but your point is still valid. What if there's uranium mixed in or something else? And you're right, you can't. You need to know the isotopics. And what you can do is you can calculate an effective spontaneous fission rate from your isotopics. And then, so typically, if you look at neutron measurements, and again, this is a little bit outside of the scope of this lecture, and I commonly think of this lecture fitting in a context, but that's discussed, is that you cannot make an absolute mass measurement with neutron coincidence counting. You need to know the isotopics. So you need neutrons plus isotopics. And that's not uncommon. You need calorimetry plus isotopics. TGS plus isotopics. That's common, because you can't.
When you illustrated the graph and showed the exponential of the reals in the beginning, it's a nice picture and everything, but obviously it has to be large enough to go beyond the statistical fluctuations that are there. So one of my questions would be, how much real data do you need compared to the background to actually see a viable signal with good error?
And we calculated at the end. I mean, you calculate that basically from your reals and accidentals rate and your basically from your reals and accidentals rate and then your accidentals rate. So you can calculate that experimentally. In fact, in the fundamentals course, you do this stuff. You stick some material in there and you figure out you can calculate the optimal gate width depending on the die-away time of the detector. And then you're right, you have a background rate, which I ignored for this discussion here. And you do have, if you have high alpha, then you have an even a more severe effect due to the higher alpha N rate. But it even gets worse. Consider active coincidence counting. Active coincidence counting has a random americium lithium source driving in random neutrons into it so that the accidentals rate is huge by comparison. So you can do it by a case-by-case basis that way. Now from the coincidence theory, you can't directly calculate your question, theoretically. You can for multiplicity counting, and Norbert Enslin did that in his seminal paper on the errors, errors in multiplicity counting. And the graph that I showed, I've written a code that implements the Enslin figure of merit, and anybody in the group is welcome to have it. Email me and I'll send it to you, where you can calculate that using his formulas as well. And you can read his paper in terms of the details of it.
So if you don't know exactly plutonium isotopics, then you cannot determine the mass of plutonium.
Yes.
And we will never know the isotopics of plutonium.
Yes, and the way that you really frame that question is you frame it as that the total error, total measurement uncertainty is the quadrature sum of your isotopics uncertainty plus your neutron measurement uncertainty.
Yeah, although Joseph, the context you're talking about, we can get close by knowing the 240 to 239 ratio. It's not perfect.
No, we will never know this. We will know this only whether it is over the threshold or below the threshold. I'm talking PPRA situation.
Well, PPRA, you're not doing a neutron measurement, so
No,
you'll never know the
but
mass
I mean,
anyway.
my question is, provided that I don't know the plutonium isotopics because it's sensitive information from Russia, I know only that the ratio is such that it's known as a weapon-grade plutonium, which may be 0.8 or 0.10. I don't know how exactly it is. And provided that I propose to use the neutron counter to establish the mass of the object of here.
You have to do the calculation of the mass behind the information barrier. That's been the presupposition of all of our attribute measurement systems, is that there's a computer handling the classified information that does the calculation, that then we do a comparison to a threshold.
Another way of doing it is you can bound the uncertainty in the isotopics. If you have I mean, when you say you don't know the isotopics, it's clear that you don't have zero information about the isotopics. You have some information about the isotopics, but there's some significant uncertainty. And the point is that your total measurement will be a reflection of the quadrature sum of that uncertainty, however it is that you ascertain it, and the neutron counting uncertainty as well, as another way of looking at it. The other way just is to actually have the measurement. Any other questions? Okay, we're done. Thank you very much.
Okay.